Hi everyone. Let's have a discussion on inductance of three-phase double circuit with symmetrical spacing. Okay. Previously we have discussed inductance of three-phase. Okay. Three-phase means we are using three conductors, but it is a one circuit. Three-phase is a one circuit. Okay. Here we are using three-phase means three conductors for the double circuit. Here three conductors for one circuit, three conductors for the one more circuit. So six conductors for the double circuit. Okay, three conductors for the one circuit, three phase, right? Three phase for the one more circuit, three conductors, that is double circuit with symmetrical. This is a symmetrical spacing, means previously I discussed three phase circuit for the symmetrical, that is for LA, LB, LC all should be same, right? Here also for the double circuit, three conductors for three phase, all flux and all inductance should be same, we'll get here. Okay, so here considering three phase double circuit with conductors placed at the vertices. Here see here vertices of the hexagonal which is shown here. Whatever x, y, z, three conductors, it makes a one circuit, and one more circuit that consists of x dash, y dash and z dash. Okay, this is gives the one circuit, one three phase, and this is a three phase, one more circuit. So we call it double circuit. All six conductors are placed at the vertices of the hexagons. Okay, six right hexagon vertices of the regular hexagon. Okay, next conductors x, y, z makes one circuit, and this makes second circuit. So we are going to find here flux for the x conductors. Okay, similarly we'll go for the y conductor and also z conductor. Okay, first we have to see x conductor flux at the x conductor is, first one is internal flux, that is flux itself, and then flux due to y conductor, then flux due to z conductor, then flux due to x dash conductor, then flux due to y dash, and flux due to z dash. These are the what external flux linkages at the x conductor due to the all five conductors. Okay, see here the distance between the conductor is d, capital D, symmetrical spacing, right? Symmetrical means distance between two conductors should be same. X, y distance is d, here y, z distance d, z x dash d distance, here is d distance, and here d distance, here also this hexagonal, right? Hexagonal, all vertices consist one conductor, so distance between them is d, capital D, same. Then here I am going to find the flux due to y conductor. We are taking distance capital D. Then at x conductor due to z conductor, external flux, that is distance between them we have to find here. Then x dash makes an flux on the x conductor. We have to take this distance, right? So here is directly to take this distance, here the capital D, but x and x dash distance is how much here is, that is 2d. See here d plus 2d d plus t, that is 2d distance between x and x dash, right? So this is the what 2d distance, and here is d distance. Then how much this distance? Find the resultant here. So 2d plus d whole square, that is okay, that is root 3 of d. So find this distance by using these two. You will get this is a root 3 times d distance. Here the resultant is 2d. 2d square is equal to d square plus this unknown. Okay, so 2d whole square means 4d square is equal to d square plus unknown. Therefore unknown is equal to 4d square minus d square. You will get the 3d square. Therefore d is equal to root of 3 and d. Okay, therefore d is equal to root 3 into d. So we got this right. So flux linkage at the x conductor, we have to write the equation here. See the equation. Flux at the x conductor, common is 2 into 10 to the power minus 7, take it common here. Current into distance of the x conductor and the distance between x and x dash. This is okay, this is fully the x conductor, and this is the y conductor, this is the z conductor. Here it is having a double circuit, therefore two equation in a bracket. Okay, double circuit for the x 2 equations, y 2 equations, z 2 equations. Okay, we have to take Ix current common, Iy current and Iz current common here. Due to X, Y, Z, we have to find the flux at the X conductor. Okay, Ix is common here. First is ln of 1 by R dash X conductor internal flux itself, right, plus ln of 1 divided by 2t. That is here first is internal flux, then due to the X dash flux linkage between X and X dash, we have to take here distance between them is 2d, therefore 1 divided by 2d. Then due to Y conductor, take it Iy current common. This Iy current makes a flux on the X conductor, therefore due to the Y conductor 1 divided by d, and due to the Y dash 1 divided by root 3d. See here, at X conductor due to Y conductor makes a flux, the distance between them is d, and here Y dash is where, here is Y dash here, right, this is the Y dash, here distance between them is root 3d. How it is root 3d? Here this is a 2d and this distance is a d. Okay, therefore this is the unknown. Unknown is equal to what? 2d plus d, that is 3d. 2d square plus d square. We have to find the unknown here, right? So whatever you have done like this, we have done here, same thing you have to do here also. Okay, distance between X and Y dash is root 3d. Okay, therefore Y conductor 1 divided by dy, and this is the Y dash distance 1 divided by root 3d. Then due to Z conductor flux linkage, this is the Z and this is the Z dash. Therefore Iz take it common here. Ln of Z conductor, where is Z conductor here? Ln of 1 divided by root 3d and plus ln of 1 divided by distance between them here is 1 divided by d. Okay, so this is the what? Flux at the X conductor. This is X conductor itself, internal flux. This is X dash distance. This is the Y dash. Then this is X, Z and Z dash. So next is what here? See here, Iy and Iz line term both sides is same, right? Take it common here. Make it Iy plus Iz. Okay. So as you know that symmetrical condition, we have to assume that all should be equal to 0. Current Ix Iy plus Iz is equal to 0. Therefore Iy plus Iz is equal to minus Ix. Put here Iy plus Iz is equal to minus X. Substitute here. Ix take it common here. See ln plus ln. So multiply here ln into bracket 1 divided by d into 1 divided by root 3d. It will get ln of 1 divided by root 3d square. Okay. Next, Ix take it common here. Ln of this term minus ln of this term. Okay. Ln of 1 divided by 2d r dash divided by 1 divided by root 3d square. Therefore, root 3d square comes in the numerator and root 3d square divided by 2d r dash. D get cancelled here. You will get root 3d divided by 2 r dash. Okay, this is the what? Flux at the X conductor. Inductance at the X conductor is flux divided by current of that conductor. Here X conductor we are taking, right? So current at the X conductor is Ix. So this is the take it Ix here. Ix get cancelled. So this is the what? Inductance at the X conductor. So as the all conductors are in parallel, so X and X dash, there are two circuits, right? Double circuit. Hence, the total flux of the X conductor, that is X dash, is 2 into Lx. Okay. Similarly for the Y conductor and Z conductor also.